This is part of our video series on human-centered evaluations for NLP explanations. Check out the link for more resources. You're currently here.
An alternative approach to human-centered evaluation of model explanations is to solicit human annotated explanations and use them as a gold standard for model explanation. The idea here is that because many labels in NLP are defined by human annotators, then human-provided explanations for those labels should have a similar claim on legitimacy as a gold standard for model output. Here we have a couple of examples of human annotated explanations from the ESNLI dataset. As you can see, these things can take on different forms, including feature attribution and natural language. Before we try to use these human explanations to evaluate the model explanations, we first have to collect them. This is a nuanced process with a lot of design considerations. This is a nuanced process with a lot of design considerations. These include what kinds of explanations we're collecting, the interface and instructions used by the human annotators, and the various ways that we control for quality in what we collect. Sarah Wygriff and Anna Morosovic have a very nice recent survey of existing human explanation datasets in which they discuss some of these issues. Before I discuss these design issues in the abstract, I'm going to go through a few prominent examples of explanation datasets in order to give a concrete idea of what these things look like, as well as the interfaces used to collect them, where that information is available. The first one that I'll mention is the BeerAdvocate dataset released by Julian McCauley in 2012. This dataset took a small sample of an existing dataset of multi-aspect beer reviews and had human annotators identify the sentences in each review that pertain to each aspect, those aspects being the taste, smell, and appearance of each beer. And here is an example of the result taken from a later paper. You can see here that the review covers multiple aspects of the beer, only some of it pertaining to the appearance specifically. The next example is the WikiAttack dataset, which was similarly sampled from a larger existing dataset, specifically the WikiToxic dataset published by Jigsaw in 2017. For this explanation dataset, annotators were asked to explain whether each comment had personal attacks in it by highlighting all of the personal attack spans within each comment. The result looks like the following, with each individual personal attack identified within the text. This dataset was collected using the BROT NLP annotation tool, which has been historically popular but is a little bit dated now. MultiRC, by contrast, is a reading comprehension dataset where the explanations were collected alongside the document-level labels. Each MultiRC example looks like the following: a multi-sentence document, a question about the document, specifically one that requires information from multiple sentences to answer. And then the explanation here is the sentences needed to answer the question. This dataset was collected in a two-step process. First, annotators were asked to generate claims grounded in multiple sentences. Then the claims were validated by having a second round of annotators try to answer them with only the designated sentences. Another recent reading comprehension example is Fever, which involves verifying or refuting claims extracted from Wikipedia articles. Many of these claims require reasoning over multiple documents, as in this example, although some do not. By contrast with MultiRC, Fever actually provided sentences to annotators, asking them to generate claims from them, but like MultiRC, it involved a second validation step, asking other annotators to review the claims and their supporting sentences. All of the previous examples have been rationale or feature attribution style examples, which identify the tokens or sentences from the input as explanatory. The next few examples I'm going to show you here include natural language or free text explanations alongside or instead of those rationale style explanations. The first such example is Kaushik, which asks annotators to provide both rationales and free text explanations justifying multiple choice answers to common sense questions. These three instances show the format. You can see here that annotators provided both explanatory rationales as well as free text explanations to their chosen answer. ESNLI is a textual entailment dataset asking annotators whether a premise sentence entails, contradicts, or is neutral toward a hypothesis sentence. Like Kaushik, annotators were asked to provide both rationales and free text explanations for their labels. One difference in ESNLI was that the free text explanations were required to contain the tokens highlighted in the rationales, which is kind of an interesting quality assurance mechanism. Here are several examples. As you can see, each free text explanation includes the tokens highlighted in the premise and hypothesis sentences, which will definitely have the effect of anchoring them in the input, but leads to some slightly awkward grammar in those free text explanations. Finally, the Contrastive Edits dataset released by Kaushik et al. 2020 collects counterfactual explanations in the form of free text modifications to the input text, designed to flip the label of each text. In this dataset, annotators had free rein to edit the content of the input in order to change its label. In the paper, they report a number of types of edit that annotators made, including these three examples here: inserting modifiers, replacing modifiers, and diminishing via qualifier. This dataset used a very simple interface for collecting these contrastive edits, just a free text input prompted by the original review. So I've shown you 6 examples of explanatory datasets, exemplifying different approaches to these design considerations in collecting this type of data. Now I'm going to briefly talk about each design consideration one by one. As we've seen, most explanations collected are of the rationale style, identifying key tokens and sentences in the input that are relevant to the document level label. But free text explanations are also increasingly popular. Unmentioned in this tutorial, but discussed in Sarah Wygriff's review, are so-called structured explanations, consisting of sets of rationales or free text locked into a particular format appropriate to the medium. Finally, example or case-based explanations don't really have a presence in this literature yet, at least not under that name. Gold standard explanatory examples for classification decisions do exist for particular tasks, such as identifying precedent for legal decisions, or identifying relevant documents in multi-document question answering. But these tasks haven't yet been collected together under this particular conceptual umbrella. And of course, there is a lot of conceptual overlap between the idea of gold standard explanatory examples and other families of methods based on retrieval, such as nearest neighbor-based classification, information retrieval, and recommendation. Annotator instructions are another big design consideration in collecting this type of data. In some tasks, we directly ask annotators to justify the label using explicit why language. An example is ESNLI, where annotators were directed to identify the tokens that justified the entailment or contradiction of the two sentences. In others, we can use task-specific language to solicit explanations that are arguably explanatory by construction without using explicit causal language. An example is the personal attack detection task, where we ask annotators to identify all personal attacks as a way to justify the label of contains personal attack or not. In both cases, there is a distinction between asking for a comprehensive explanation that includes all of the available evidence versus a sufficient explanation that consists of just enough information to justify the label. In the personal attack detection task, we could have asked annotators to identify just enough personal attacks to justify the label. But for our downstream purpose, we decided that we wanted to target more comprehensive explanation. Finally, a somewhat different approach is the idea of contrastive explanations, where we ask annotators to change the input in ways that they think would change the label. The Contrastive Edits dataset is an example of this. The range of approaches here reflects the selectivity and heterogeneity of explanations that Tanya mentions in her section of the tutorial. As she also mentions, however, there is a common theme here of soliciting some kind of causal or contrastive reasoning, whether explicit or in a task-specific way. Creating and deploying an interface for collecting explanations is often a hugely labor-intensive part of the process, but it's one that does tend to get glossed over in the actual write-up of the project. While there are NLP annotation tools out there, the most common way for researchers to do this is just to create their own ad hoc system. This might suggest that we need some kind of standard tool for collecting this type of annotation, but what I think it more strongly suggests is that authors should really be including this information about the collection interface in the paper, and making the code associated with the interface and the collection experiment available alongside the data and whatever modeling code that they might have. Controlling quality is another very important design consideration. Crowd workers, as many of you will know, have a lot of issues that can lead to low quality results. Like normal NLP labeling, one solution is to simply collect multiple annotations per item. But because explanations are a very particular type of product, there are particular ways that we can validate them depending on the properties that we want them to hold. If we want, for example, explanations to contain sufficient information needed to predict the true label, we can do as MultiRC and Fever did and evaluate this directly using a second group of annotators. We can also apply common sense heuristics, like that the free text explanation should contain the rationale tokens without otherwise being too similar to the input, as was done by the ESMLI team.
This video isn't the end. You're currently here. If you're lost, click on the link below for source code, slides, and other resources.